Hi there, in this video we are going to discuss the chain rule and when it's used. So the chain rule is used when we have a certain operation of functions. So let's go over all the different operations. We can add and subtract functions. So when we take the derivative of addition or subtraction of functions, we just add their derivatives. Right, the derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. When we have the product of two functions, then we use the product rule. And so we include that in here. So the derivative of the first, the second left alone, plus the first left alone times the derivative of the second. And so that's the product rule. The quotient rule is when you have division of two functions. So, and this is our quotient rule. So then when do we use the chain rule? Well, there's one other operation that we haven't discussed, and that is the composition of functions. So how do we find the derivative when you have composition of functions? And so that is where the chain rule will come in. So the chain rule is used when we have composition of functions. So let's look at one example. So find the derivative of g of x equals 2x plus 5 squared. Now here we can just, we don't need to write this as a composition of functions. We can just say g of x, I can rewrite it as 2x plus 5 times 2x plus 5. And so I can either use the product rule or I can continue simplifying and get 4x squared plus 20x plus 25 and then take the derivative. Right, so this will be 8x plus 20 and then that will be done. But notice that this is a composition of functions because I can say that g of x is really, what can we say, like you have a composition of two functions. So say y equals x squared and u equals 2x plus 5. So then this is, g of x is the composition of y of u. So right into x, you have plugged in the 2x plus 5. So let me write it properly. Y will be equal to u squared. So into u, you have plugged in 2x plus 5, and that's how we get this composition. So the idea is then, how do I still get my 8x plus 20? And you might be thinking like, why do I need to write it as a composition when I just multiply it all out? Well, what if our exponent was different? So what if I had, instead of 2x plus 5 squared, 2x plus 5 to the 10th? Now here, 2x plus 5 to the 10th, that would mean 2x plus 5 times 2x plus 5 10 times. And I don't want to have to multiply that out. So that's where the chain rule and seeing this as a composition of functions really comes in handy. And so what is the chain rule? So we'll use the same functions that I used above. So let's say, let's let y of u equals, in this case, it will be u to the 10th. And then my u of x will be 2x plus 5. So now notice how when you compose this, you are going to get that h of x, right? So h of x is really y of u of x. Does that make sense? Let's see, let's check it. When you find a composition, right, y is u to the 10th, so everywhere you see a u, you're going to plug in your u of x. So this will be, then h of x is u of x, right, to the 10th power. But u of x is 2x plus 5. So this is 2x plus 5 to the 10th. So that's how we're essentially going backwards. We have this function, we're trying to see what was composed in order to get that. Now the derivative, when I take the derivative with respect to x of this composition of functions, what are we going to get? So we're trying to take the derivative of h of x. So the chain rule then says, because h is the composition of these two functions, y and u, the derivative is going to be then the derivative of y, the first function, the outside function, with respect to y is a function of u, so with respect to u, then times the derivative of u, the inner function, with respect to the variable, right? U is a function of x, so du dx. And so this is what we call then the chain rule. So now breaking down this function, that means that the derivative of our function 2x plus 5 to the 10th is going to be the derivative of y with respect to u. So the derivative with respect to u of y is u to the 10th, times du dx, the derivative with respect to x of u, which is 2x plus 5. And so now we take the derivative. Now here I can just use the general power rule. So this is 10u to the 9th times the derivative with respect to x of 2x plus 5. So that would just be times 2. And now plug in what u was, right? Notice up here, u is 2x plus 5. Up here, u is 2x plus 5. So now I substitute my value of u. And make a note here, u is 2x plus 5. So we substitute that in. So I'm going to have 10 times 2x plus 5 to the 9th, and then times 2. So our final answer is 20 times 2x plus 5 to the 9th. So that will be our derivative for this function. Now notice that if I do the same thing here, do I still get the same answer? So using my composition of functions here, right? So this is g, so that means that dg dx is going to be dy du times du dx, according to the chain rule. So I'm going to have the derivative, right, of the function that I want is going to be dy du. So y is u squared, so it's d du of u squared times du dx. So the derivative with respect to x of 2x plus 5. Running out of room here, but I think we can make it work. So what's the derivative of u squared? This will be 2u times, and then the derivative of 2x with respect to x is 2. So I get 4u. Now remember, what was u? 2x plus 5. So this will be 4 times 2x plus 5. And notice that here, if I factor out the 4, I get 2x plus 5. So they are the same answer. The chain rule is just allowing me to essentially have a shortcut. Instead of having to multiply this out, right, because this will be 2x plus 5 times 2x plus 5 times 2x plus 5 10 times. I don't have to do that. Instead, I can use the chain rule, which is really nice. So that then we don't have to do that crazy multiplication. And so that is what the chain rule does. So it allows us to take the derivative of compositions of functions. Let's try another example. So let's try this example. Let h of x be 4x cubed plus 1 to the 3rd. So the part A is identify functions such that, essentially so that we have a composition of functions. So what two functions are being composed is what this is asking. So identify y, that's the outside function, and then u is the inner function. So what are the two functions being composed here? So for part A, we're going to say let y equal, so what is happening here? I have something cubed, right? As soon as I see that, oh, I have a quantity cubed, my outside function is the cubing. So this is going to be u cubed, and u then is the inner function. So u is equal to 4x cubed plus 1. So when you compose these functions, you're going to get the original h of x. So those are my two functions. Now the derivative of h of x, so that means that h prime of x is going to be the derivative of the outside function. So the derivative of y with respect to u, because that's a function of u, times the derivative of the inside function u, and u is a function of x, so with respect to x. So one way that you can think of it too is that, right, a function, so h of x, f of x, g of x, those are all fancy names for y. So another way you can think of this is that you're trying to find dy dx. So notice that dy dx then is equal to, in this case, dy du times du dx. Notice that our du's cancel, right, leaving us with dy dx equals dy dx. And so that's essentially what we're doing, and we're doing this composition, but the insides kind of, in this Leibniz notation, they cancel out. So this is called Leibniz derivative notation, which is kind of like dimensional analysis. It helps us see that these two are, the left side is actually equal to the right side by doing that cancellation. But it also helps us then, the derivative, now that I can find it, so the derivative of our h function, so h prime of x, is dy du, so y is u cubed, so what's the derivative of what? U cubed. And then times du dx, so the derivative with respect to x of u is 4x cubed plus 1. So notice that when I'm taking the derivative with respect of, right, so dy du, my variable inside matches the variable that I'm taking with respect to, right? D du, this tells me the function should be with respect to u. D dx, that tells me my function should be with respect to x there. So now h prime of x will be the derivative of u cubed, which is 3u squared, times the derivative now with respect to x of 4x cubed. So that's 12x squared. And now we want to put it all in terms of x. So replace what u was. What is u equal to? And for that, we go back up here. U is equal to 4x cubed plus 1, our inside function. So this becomes, so h prime of x is 3 times 4x cubed plus 1, what u equals, square, times 12x squared. And now I can simplify this, which is this 36x squared times 4x cubed plus 1 squared. So notice that a shortcut to this is essentially, instead of having to write out the individual functions and what the composition is, I can look at this and say, oh, looks like I'm doing the derivative. So let me write it out. Let me write the original function again. So I know h of x is 4x to the third plus 1 cube. So how can I get this derivative without having to write out the individual compositions? So it looks like what I'm doing is I'm identifying the outside function. So the outside function is the cubing. So I take the derivative of that. So the derivative of something cubed is bring the exponent down and then is square, right? But notice that the inside stays the same. So I'm going to leave 4x cubed plus 1 there. And then times the derivative of the inside, so times 12x squared. And so that is what we're doing. So in general, without having to do the individual writing out the compositions, we can say if I have f of x equal to, let me change it, let's say h of x. If I have h of x equal to f of g of x, right, the composition of two functions, then h prime of x is the derivative of the outside function. So the outside is f, so it'll be f prime, the inside left alone, times the derivative of the inside. times g prime of x. And so this is what most books have as the chain rule. But it's important to recognize still what the compositions are to better understand what we're doing and what the outside and the inside functions are. So this is our chain rule. So it's important to know what is the outside function, what is the inside function. And another thing, right, this is composition. This is not multiplication. I'm not doing f prime times g. This is composition of functions. Now, without doing this, finding the y and the u, let's try an example using the shorthand version of the chain rule. All right, so let's try this example real quick. Find the derivative of h of x equals the square root of 3x squared plus secant x. So this is definitely a composition of functions. So the question is, what's the outside function and what's the inside function? So I'm going to rewrite this in a way so that I can see what my outside functions are and my inside function. So h of x is, so this is going to be 3x squared plus secant x quantity, right, to the 1/2. And so now I can see, oh, my to the 1/2, that is the outside function. And what's the inside function? Then this here is my inside function. So when we say up above, let's see, we had h prime of x is the derivative of the outside, the inside left alone, times the derivative of the inside. It helps to figure out what's your outside function, what's your inside function. So so the chain rule says for h of x equals to f of g of x, h prime of x is f prime, the derivative of the outside, the inside left alone, times the derivative of the inside. So for our particular function then, h prime of x is the derivative of the outside. So how do you take the derivative of something to the 1/2? So it'll be 1/2, the inside left alone, and then reduce the power by 1. So 1/2 minus 1 is negative 1/2. The inside is left alone. And then times, now I do the derivative of the inside. So now we're going to do this derivative. So what's the derivative of the inside? What's the derivative of 3x squared? 6x. And I have two terms, so make sure you use parentheses. And what's the derivative of secant? The derivative of secant is secant x tangent x. And so that is my derivative. I can't simplify too much. I do have a negative exponent, so we're going to bring that to the bottom. So I'm going to have a 2 on the bottom and then this quantity. And what stays on the top is the 1 and that quantity. So I'm going to have 6x plus secant x tangent x in the numerator, and then the denominator, this 2 from the 1/2, and then this is coming downstairs, 3x squared plus secant x to the positive 1/2. So that is as far as we can go. The only thing that I'm going to do is write that 1/2 as the radical. And this will be my derivative, right? So in short, or to summarize, the derivative using the chain rule is you take the derivative of the outside function, the inside left alone, then times the derivative of the inside, which means you have to be able to recognize that you have a composition of functions first, and then which one is the inner function and which one is the outer function, because outer functions you take the derivatives of first. But oftentimes you'll have more than two functions being composed, right? So like for example, and we'll do this in the next video. Say I have h of x equals something like the square root of secant 5x plus 1. Now here, I'll give you a hint, there are three functions being composed. Can you spot what they are? And in the next video, we'll start with that example.